The question that brought me to the stage today is how do we approach performance issues? First of all, we notice performance issues during incidents. This is just harsh reality of life. And we have to deal with them while we are stressed, overwhelmed, and as the famous saying says, under pressure, we do not rise to the occasion, but we sink to our training. And in our profession, our training is how we think, and that's why it is important to have mental frameworks ready and available for us to deal with issues. And so I hope to give you today such a framework, which is based on my experience with TimeCapsule. My name is Dmytro. I've been with Wix for more than 3 years. All this time, I worked for Server Guild in the Kostiuchenko team. I wrote code for many companies and organizations like Google and the National Institutes of Health. I contributed code to popular open source projects, and I'm also a big fan of Nix and NixOS. So if you are too, please let me know. What the hell is Kostiuchenko, or as people who don't know how to say it, say Kostiuchenko. So Kostiuchenko is a variety of grape which is grown mostly in Italy. The wine from this grape is known for its full-bodied and bold taste and rich flavor. And also it is an infra team where I work along with 4 other amazing engineers, and TimeCapsule is one of the products we maintain. So what is TimeCapsule? TimeCapsule is a distributed task scheduler, but you can think of it as a reminders application on your Mac or your iPhone, but it is meant to be used by other applications. So it has an API with methods like schedule task and delete task. When application creates a quote-unquote reminder, it makes a call to schedule task endpoint, and then TimeCapsule writes this task to the database, and the application can continue doing whatever it was doing. In the meantime, TimeCapsule wakes up once per minute, checks if there are tasks scheduled for this specific minute, reads those tasks from the database, if there are any, and usually there are many, and then sends this task to a Greyhound topic dedicated for this application. The application then consumes those tasks, and that's how it is being reminded about the action it wanted to perform. And of course, the system is multi-tenant, which allows multiple applications to schedule their own tasks. Some conventions before we proceed. I'm going to talk fast, or I'll try to talk fast, because we have a lot to cover. And that's why I will skip over some details. And sometimes, therefore, I will make claims which may seem controversial. And if this happens, you'll see a ribbon on the top of the slide. It means roll with it. If you're interested, you can ask me later, and I'm sure I will be able to show you that these claims are true for TimeCapsule. I will tell you 4 anecdotes related to TimeCapsule performance. And from those anecdotes, I will make 5 insights. 2 of them will be technical, the rest will be methodological, and together they will form a framework. And so I'll start from the middle of the timeline. It is year 2023. TimeCapsule is already a performance reliable system. We have implemented most impactful techniques for improving its performance. And it performs great mostly, but the part of the flow where TimeCapsule wakes up once per minute, reads tasks, and sends them to Greyhound, it can't finish in time 1 out of 60 times. Why so? This is because certain minutes are much more popular than others. Think about alarm on your phone. It is likely set to something like 7 a.m. or 9 a.m., but not 8:59. So the same happens for TimeCapsule. Luckily, we have measurements. We measure everything, and we see that the slowest part of the flow is producing tasks to Greyhound. This is this part of the flow. And so we decided to tackle that. We read about Kafka optimization. We learned about a technique called producer lingering. Lingering allows producer to wait before sending tasks on the wire, combine them in a single batch, and send them together, because supposedly this is more efficient. This awaiting, this lingering, is configured by 2 parameters, by time, is parameter linger ms, and by data, this is the other parameter. And so we, in our code, we already measure how long it takes for a task to be produced. This is so-called, of course, a pseudocode, but the general idea stands. So we measure that, we emit that as metrics, and then we display this on Grafana. And having this graph, we start changing producer parameters, and we change, and we see nothing on our graph, like totally nothing, like zero, nada. So let's figure out what's wrong. First issue to notice is that it takes around 2 milliseconds to produce a task, but we measure with millisecond precision, which means that the improvement or degradation has to be at least 500 microseconds to be visible on the graph. OK, let's assume that we fixed the precision and we start measuring with high precision. What's next? In order to display our measurements on Grafana, because monitoring infrastructure works with 1-minute granularity, in order to display those measurements on Grafana, we have to aggregate everything in 1-minute bucket. And typical choices for aggregation functions are mean or average, median or P50, some higher percentiles like P99 or P95, or max. And maybe I'll do a quick quiz. What do you think is the right function for us to display latency on Grafana? If you think it's mean, please raise your hand. OK, if you think it's median, if you think it's P99 or P95, and if you think it's max. OK, so I'm sure, yeah, everyone in some point in their career, they had read something like this, that mean is meaningless, pun intended, use P99. And that's what we did, and this makes sense for latency. But now let's think what is going on. So we measured latencies of, produced latencies of individual tasks. We dropped 99% of those measurements, took only 1%, this P99, right? But in the beginning, we were trying to improve how many tasks we produce in a minute. So we were thinking, like we were trying to improve our throughput, but we were measuring latency. And it's not just latency, we were measuring inaccurate latency, and we were also applying a nonlinear function to it. So there is no correlation between what we measure and what we're trying to improve. And so the first insight from this anecdote is define what do you mean by performance. Because performance is a very abstract word, and different performance metrics require different techniques, which sometimes conflict with each other. Improving throughput may hurt latency, and vice versa. So in TimeCapsule, we're interested in throughput, and that's what we're going to talk about today mostly. The first technique that helped us increase throughput is batching. The story with producer lingering is an example of batching, and why should it work? The idea is, like, first of all, when Kafka sends a message on the wire, there is some overhead connected with internal processing, with networking, and the idea is that if we combine the messages in a single packet, we'll pay the overhead price once, thus making the entire process more efficient. So lingering should have worked, but even after we fixed our measurements, it didn't actually work the way we expected. This is because the actual diagram for lingering looks like this. Producer in TimeCapsule, because it has multi-tenancy, it sends tasks to hundreds of topics, each having multiple partitions. And so producer connects to multiple brokers. And if messages in the queue are targeted to different brokers, it means they cannot be combined in a single batch. It's really obvious in hindsight. And so right now in TimeCapsule, we have a piece of code that ensures that messages are ordered in such a way that batching becomes possible. And lingering does work. And when we implemented that, we saw a noticeable, with an asterisk, this is important, I will come back to this later, noticeable gain in throughput. There is another example when batching helped TimeCapsule throughput, but for a different reason. So a part of its public gRPC API, in TimeCapsule, we have private Greyhound-based API. So many clients, most of the clients actually, and this is transparent to them, instead of calling gRPC API, they actually send special messages to special Greyhound topic let's call them commands. And TimeCapsule consumes these commands one by one and processes them as if they were calls to gRPC API. At some point, we started having performance throughput issues with this consumption, so we switched TimeCapsule to consume in batches of 100. Of course, the idea was that by consuming in bulk, we save on overhead cost, like in previous case, but also consuming in batches gave us some wider context. And important details, TimeCapsule API is idempotent, which means that you can schedule the same task many times, and the last call will always matter. And applications actively utilize this property. And for example, a user may click on UI in a rage 20 times some button, and the application will schedule the same task for 20 times. And that's what we discover, that in those batches, we have duplicates, and sometimes we would even have a delete command for the same task in the same batch. And if this happens, there is very little work for TimeCapsule to do. And so by discarding duplicates, we achieve up to 50% compression, which means half the number of expensive calls to our database and external services. And overall, this gave us more than 10-fold increase in throughput. So the insight here is very simple. If you care about throughput, use batching, because it's great for two reasons. It saves on overhead costs, and it unlocks higher-level optimizations like compression. Of course, no technique is a silver bullet, and the next anecdote from our experience proves this. When TimeCapsule wakes up once per minute to process tasks scheduled for this minute, it has to account for many edge cases, many variables, because we have many retry flows imposed from the server. We have many cancellation and cleanup flows. We have very complicated task lifecycle. And another implementation detail, when TimeCapsule reads tasks from the database, it actually performs an update first. And this update is a very large single query on a database, which has to account for all those edge cases. Essentially, we have like a part of business logic implemented on a database side. When I first saw this, it was very easy for me to explain this to myself. So first of all, why single query? Because single is better than multiple, because we save on overhead cost. Why complicated? Well, because databases are great with crunching data, and probably MySQL would do a much better job than me writing some trivial Scala code. And as a bonus point, single query is an atomic operation which helps with reasoning. And I didn't have to think about this more until we migrated to MySQL 8. And that's when suddenly we started having deadlocks. So what happened, when TimeCapsule was executing this expensive single update, MySQL would detect a deadlock. And in TimeCapsule, we would see an exception thrown by JDBC driver, which of course breaks our entire flow. So as a hotfix, because it was an incident, as a hotfix, we introduced try-catch, and we started to try in the failing query. And after we GA'd this, we unexpectedly saw that there is no degradation in performance in any metric. Well, so TimeCapsule works as before. And we thought, well, maybe it's some false positive. Maybe MySQL is wrong. And so we left this try-catch and retry in the code for some time, until DBAs reached out to us and said, hey, guys, you have deadlocks. This is very bad. But we still brushed it off as something unimportant. And this is the point where I would like to thank our DBAs for their persistence. Again, pun intended. Because these guys convinced us that we have to split our big query into multiple queries. And indeed, after we did that, we discovered that we no longer have deadlocks. But also, unexpectedly, we saw noticeable gain in throughput. Again, noticeable with an asterisk. I will come back to that later. And again, it's really easy to understand in hindsight. If we have two transactions, they are very narrow and small. Database can execute them in parallel. But if transactions become wide, there may be a conflict. So database has to serialize the execution. And also, if transactions are complicated, meaning long-running, then this really starts hurting performance. And by this explanation, you can conclude that I am not a guru in databases. You'll be right. I'm telling you this story because I was sure that I know how our system, how it works, what's happening. But I didn't know that my knowledge is wrong. And this is a classic example of unknown unknowns. And so the insight here, you should be aware of unknown unknowns. And this is very abstract. It doesn't say much. And this is a very big topic, which deserves its own talk. There are many books. One of them is Super Forecasting. One practical advice I would like to give on this topic is the technique of 5 whys. So what it is. If anyone makes a claim, you should ask why this is true. A is true because of B. Then why B is true. And you should continue doing this until you, well, at least for 5 times, or until you reach some coherent chain of reasoning from your final claim F to your original claim A. And this would mean that probably your claim A is true. Or you may discover some contradiction in your reasoning. And this would mean that claim A is probably false. Application of this technique is actually harder than it seems. For example, I could say we should keep the single query. Why? It's easy, because single query saves on overhead costs, database is great with data, with crunching data, everything. You saw that this doesn't work, because the question is easy, we know the answer, and this locks us in the realm of known. We remain susceptible to our biases, so this doesn't work. Alternatively, we could say we should split the query. Why? Well, that's a hard question. First of all, it challenges our beliefs. Second, it requires effort to do a proper research. And the mere fact that this question is hard may be an indication that maybe it's a right question to ask. But there is no guarantee. So you should just practice, and you'll become better at it. But, I mean, that's hard. Yeah, and I think that's it with batching. Yeah, that's it with batching. Let's talk about another technique that helped TimeCapsule quite a lot. That's sharding. Initially, when we inherited TimeCapsule from different team, it was designed as a so-called single worker system. Every minute, one instance of TimeCapsule would wake up, process all the tasks scheduled for this minute. The next minute, another instance would wake up, but it always exactly one instance. So eventually, we had to split the set of tasks into smaller subsets and wake up multiple instances to allow for concurrent processing. And this is the idea behind sharding, and specific details are out of scope for this presentation. I will show you the metrics. This is from year 2021. When we implemented sharding. So before we implemented sharding, it took TimeCapsule 3 minutes to process 80,000 of tasks. After we implemented sharding, it took only 6 seconds. So it's more than 30x improvement. Oh, yeah, thank you. Long overdue, it was year 2029. Yeah, thank you. Small technicality about sharding is that in TimeCapsule, sharding costs us money, and it has performance overhead. Again, this is like details I cannot cover right now, but we have this trade-off. If we pick the number of shards very large, we can flexibly scale, but the solution will be expensive, and we'll have overhead, which will potentially cripple gain from the sharding. Or we can pick the number of shards very little, and we'll have limited scalability, but the solution will be cheap and overhead. This was a very easy data-driven decision. We knew that we wanted to increase our throughput by a factor of 10. We gave us room for improvement, so we settled on 20 shards. And that's how it worked until we implemented autoscaling. Because initially, TimeCapsule worked with only 4 instances without autoscaling. And with autoscaling, we discovered this very weird, unexpected arithmetic property of natural numbers. If we want uniform load, and we want that, we can only scale to 2, 4, 5, 10 instances. And when we scale from 2 to 4, it's double the number of instances, and 4 to 5 is only 25%. So it's uneven, and it's very bad. Now we have 24 shards, and looking back at metrics, we could have probably had 12, because we rarely scale to more than 6 instances. But reducing number of shards is harder than increasing, so we have 24. Insight here is simple. If you care about throughput, use sharding. It allows for concurrent processing, and you should think about load distribution up front. Now back to this noticeable with an asterisk. Remember from previous slides. So the truth is, I simply don't know and don't remember how much certain actions helped us. This is because we never cared to remember and we never cared to record. And so don't be like us. Keep performance optimization journal. Journaling, of course, is great for remembering things, but there is less obvious benefit is that journal is your thinking framework. If your template contains certain questions, you will be forced to answer those questions. And so before I conclude this section and the presentation, I'll do a quick recap. So first, we talked about how we should define what do we mean by performance. We also had 2 technical insights, is that we should use batching and sharding. We talked about unknown unknowns, the technique of 5 whys. And now we're talking about journaling with the right template. And so as a conclusion, I want you to offer a template for a journal which includes all those insights inside. So your journal should have 3 sections. In the first one, you state the problem and the goal. The issue is we want to, and here you define your performance metric as precisely as possible. This is our insight 0. In the next section, you describe your experiments, and each experiment you describe using 3 subsections. First, you state your intention. We intend to do batching or sharding. You can here apply technical insights. Then you state your expectation. We expect to see, and you here apply the technique of 5 whys. It's our insight 3, to explain why do you expect to see that. When you conduct the experiment, you describe what you actually saw, what you actually observe, and again, you use technique of 5 whys, especially if actual results are different from the expected ones. This is the point, like if you do this with the technique of 5 whys, this is the point where you learn new things and where you discover your unknowns. Finally, you make a conclusion, and the example of application of this template is linked on the slide. This is a synthetic example, which I made specifically for this presentation. It's based on real events, but all the real data is gone, unfortunately, so it's my best effort. But anyway, I encourage you to try this template. And if you do, I would be really, really grateful if you gave me your feedback, whether it worked, whether it was helpful. Maybe you'll have some ideas as well. And you can comment on the example that I linked. You can write me a Slack message, or you can write me an email. And that's it. Thank you.